I'm Chen. The first author is my PhD student, and the second one is Dr. Bingbing is my former student. Today, I'm from the Tianjin University in China. So today, my topic is multi-axial thermomechanical fatigue behavior of 316H stainless steel. This content I will present here. So as you know, the pressurized water reactor and NPPS has been extensively commercialized and also is a mature technology. Now, for fourth generation fastest neutron reactor NPPS being under demonstration project also in China. So that, and in the future, the fusion reactor NPPS, the temperature will be increased with this for fourth generation the nuclear power plants. So this example for sodium cold faster reactor we call the SFR. Their thermal transit condition in the original SFR, and also their thermal stripping near the cover plate of reactor core in SFR. We induce the thermal mechanical cracking of tubes in SFR. So there are several service loading conditions, such as multi-axial stress and mechanical flow induced vibration, thermal stress. So in this study, we concentrated on the multi-axial thermomechanical fatigue failure. In this study, the material 316 stainless steel is employed. This is developed for especially for the fourth generation nuclear power plant, nuclear power material. We cut the samples from the pipe with diameter of 800 millimeter and thickness of 14 millimeter. By the specimen cut from the axial direction. And we designed two kinds of the loading paths for lumbers. This with 19 degree out of phase for out of phase tension and torsion loading paths. And also we have the two loading condition for isothermal fatigue we call IF, and in phase thermal mechanical fatigue we call IP. So for IF loading, the temperature is constant. Keep the constant in the temperature in 650 centigrade. The strain is cycle. But for in-phase thermal mechanical fatigue, the maximum temperature is 650 centigrade, same with the IF loading, but the minimum temperature is about 300 centigrades. The test is run on the MTS machine with the induction core for temperature, for high temperature, and measure temperature, monitor temperature with thermal copper, K-type thermal copper, and strain controlled with extensometer, tension torsion extensometer. These examples. And after the test, we did some SCM and the EBSD observation for the specimen. We cut the specimen like for fracture surface and for second crack observation and for EBSD observation. That's for different surface and different direction. There's some results for stress response. The left figure, left two figures, is actual stress, and this actual actual stress with number of cycles, and the different stress range, and this for example IP loading, the actual stress amplitude with cycle. So you can see the for IP loading part, the stress will be higher than the IF. And also we compare the uniaxial fatigue. This left is multiaxial fatigue, right is uniaxial fatigue. So we just compare the axial stress. Because multiaxial we have the torsional and the tangent compression. So we just compare the axial stress with the number of cycles. So we can see the later that work. For multiaxial loading, the stress will be higher than the uniaxial loading. Also, this is for IF, and also for IP, the multiaxial loading is show the high stress response compared with uniaxial loading. It means under non-proportional loading, there are some non-additional hardening. And so we compare the saturated stress for all the experiments. So this is the left figure is for IF uniaxial, IF multiaxial. So you can see the saturated stress is high. It's similar the last page the results. And for IP uniaxial and multiaxial. So also you can see that multiaxial loading with a high saturated stress, and also this one is higher than this one. And for if we this multiaxial versus uniaxial, and we compare IF versus IP, for uniaxial, the IF have the high stress response, and for multiaxial loading, also the IP with the high stress response. And that's I show the hysteresis loop. This is a half-life hysteresis loop. For each amplitude, we put the track together, and so we can see that this the left figure is isothermal fatigue, IF. This IF, this actual stress. This one is shear stress. The shear stress, and then this actual stress. So you also can see that for IP, the loading with a high stress response, and also for shear stress, we can see the stress and here the maximum stress arrived, and then stress relaxed because of the 90-degree out of phase loading. Then we compare the hysteresis loop for uniaxial and multiaxial loading. This left is an IF test, the right is an IP test. So we just compare the axial stress. So you can see for IF test, for the small strain range, there are many big difference between the uniaxial and the multiaxial. But for the high strain range, it still is big, but it's not so much. And also, and for IP, we can see the difference is bigger than the IF. So let's see the fatigue life. If we compare all the data for NIF and NIP, we plot in the figure. So we can see all the fatigue life for IP is longer than the IF, and we can see the figure, and with the string range, the decrease percent, it's about 13% for this one, 0.2 string percent, and 0.3, 0.4, 0.6, it's about 40% degree the fatigue life. And if we compare with the uniaxial loading, the decrease is not so much. It's about it's about 10%, and also for different string range, they are not too much difference. And also for this figure, if we decrease the string range to small, maybe 0.15%, we guess maybe the fatigue life will be inverse this result. But it takes too much time, so we didn't finish this experiment. For this one, we take 5 days, just like the professor he said, same result. So what is the underlying mechanism responsible for the short cycle life of IF than that of IP? So we studied the microstructure deformation. We checked. We did the EBSD experiment. This for IF 0.2% and IF 0.6%, the Km values increase, right? Because the string increase. But we compare the IP and the same string range. This one Km value is larger than this one, So it's means that the overall deformation was more thorough in the IP test than in the IF test. And but you know, the results show that for IP test, the fatigue life is longer than the IF test for this material. So that's a question. And also we check the low angle grain boundary, LAGB, and also the Km. This value also show the strain, the practice deformation. So it also shows the deformation is more thorough and the multiaxial loading and the uniaxial loading than under uniaxial loading. For photograph morphology of IF, the observation shows that multi-source fracture and intergranule cracking you can find, and second crack, triple junction in the early stage of crack propagation, and intergranule cracking in the later. And we also find some thorough oxidation here. And if we compare the different different strain range for IF loading, seems creep deformation, creep damage acts as a string amplitude increase. And this for IF deformation mechanism with different string range. So also you can see the string, the Km value is increased with a string amplitude increase, and also for the IF 0.3% IP, we compare the two to picture we can see the oxidation in the surface and the green facet striation, and so it means the oxidation damage is more so in the IF test. So we can get some conclusion that multiaxial tests show more significant cycle hardening than uniaxial tests. Saturated stress in the IP test are significantly higher than that in the IF test. The cycle stress response of IF test can be divided into 3 stages, but the stress response of the IP test consists of only 2 phases. I didn't explain this phenomenon. The fatigue life of the IP test is longer than that of the IF test at all strain amplitude. The stress concentration at the green boundary is more pronounced in IP test than in the IF test. And the last, we get more grip and oxidation damage in the IF test, resulting in the low fatigue life than the IP test. But we didn't find more evidence. So the question is still open. So thank you everybody.